Hello students, in this video we'll discuss the basic properties of the solutions to the wave equation and discuss weak solutions and the parallelogram law. So let's recall we're studying the wave equation. We'll just study the one-dimensional wave equation, utt is equal to uxx, right? Here x is in r and t is greater than or equal to 0 is the 1D wave equation. And here I'm just taking c to be equal to 1 for convenience. C is equal to 1. And of course we know what's the basic scheme for solving the wave equation. The idea is that we're going to look at the characteristics. We're going to look at u and eta. Eta is going to be x plus t. And mu is going to be x minus t. And in these new coordinates, eta and nu, the wave equation becomes what? Then this implies that utt minus uxx equals 0 is equivalent in the u eta coordinates to what? To u eta mu equals 0, and this tells us, therefore, that the solution in the u eta coordinates is going to be f of eta plus g of mu, like that. And so let's think about this for a second. So that's the general solution. So of course our solution is going to be what? Our solution u of xt is going to be an arbitrary function of f of x plus t plus g of x minus t, like so. Okay, excellent. So that's the basic solution. Now, of course, one thing we can note, if f and g are just continuous, we say that that's a weak solution. Okay, because if they were just continuous, I wouldn't be able to differentiate them. Nonetheless, this structure still satisfies this condition over here by the characteristics. That's what we really want, right? And we'll think about that in the context of parallelograms in just a second. What are some basic properties of the wave equation, though? The basic properties. Here's proposition. If u of xt solves the wave equation, then so does tau y of u of xt, which is going to be u of x plus y comma t, right? So in other words, I can translate the spatial variable and I get another solution. That's clear because the x derivatives won't matter. I'll just plug in yt to both sides. The x derivative is going to be left invariant, and that's trivial to prove. So it's a trivial proposition. That's the first thing we do. So there's translation invariance in at least a spatial variable. Good. Next proposition. If uxt solves the wave equation, we can just call this over here star, solve star. Then, if u is infinitely differentiable, then all derivatives satisfy the equation. Then all derivatives of u satisfy the equation. Okay. And the last proposition we'll do before we do the parallelogram law is just the scaling, and that's an important one, obviously. So one less proposition. U xt solves star. Then u lambda of xt, which is u of lambda x lambda t, for any positive lambda, for any real lambda, also solves star. Great. So in other words, that's the scaling of the wave equation. Okay, excellent. And of course, I can multiply this by another factor sigma over here. That will still work as well, where I can scale the solution. I still get another solution. Okay, great. And so let's think about this. So what I'm going to do now is we're going to talk about this in this parallelogram law. All right. So suppose I have a rectangle over here. I have a point A. This is in the mu eta space. Okay. I have a rectangle A, B, C, D, parallel to the axes, like that. Okay. Now what can we say in this rectangle over here? Well, I know that if I plug in the point A into this function u, so u of A, okay, has to be the same as what? Has to be the same. Well, let's think about it in terms of f first, right? Let's do that first. What can I talk about f? So that's when eta is constant. So eta is fixed over here. So f of what? So eta is fixed, right? So if eta is fixed, f of A is equal to f of D, right? Because eta is going to be the same on both those things, right? And then f of B is equal to f of C, right? And then similarly what? Similarly, what can I say about G? I can say that G of A is equal to G of B, because mu is fixed there, right? And G of what? And G of C is equal to G of D, right? Good. And so now what can we say about U of A? U of A plus U of D is going to be what? Or what do I want to do? I want U of A plus U of C rather. So let's do U of A plus U of C. Let's do U of A plus U of C. Okay. So what's that going to be? So U of A is going to be f of A plus G of A. This is f of A plus G of A, right? And then U of C is going to be what? U of C is going to be f of C plus G of C. Okay. And now let's think about what those things are. So I can replace f of A with f of D, right? So that's f of D over there. Plus what? F of D, and then what's G of A? G of A is G of B. G of B. F of C is the same as what? F of B. And then what's G of C the same as? G of C is the same as G of D. Okay, excellent. So of course, these things together, what does that equal? Well, G of B plus F of B is equal to U of B. So that's U of B plus what? Plus U of D. So the solution of the wave equation, this U, so if I look at U over here plus U over here, that has to be equal to U over here plus U over here, right? And what does that translate to in the xy plane? In the xy plane, that's going to translate you to a parallelogram, right? Okay, that'd be my xy, y, and or my excuse me, not y, but t, of course, right? T. A, B, C, D. And what's the corresponding result for this wave equation over here? This would say that U of x plus h, comma, t plus k, plus U of x minus h, t minus k, has to be equal to U of what? U of x plus k, t plus h, plus U of x minus k, comma, t minus h. And so that would be the result that we would get for our wave equation over here. And it just comes from the fact that if we look at a rectangle in the U eta space, the rectangle in the U eta space translates under these characteristic changes into parallel lines, right, by this structure over here. And that will translate to the Tx space in such a way that you have this relationship. And that also enables us to define this notion of a weak solution. As long as it's going to satisfy these relationships over here, that gives me an alternate way of using this parallelogram law to prove that there's a weak solution to the wave equation. Thank you very much.